converted it into meter cube. Why we have converted it into meter cube? When you want to use it in liters, otherwise you can keep it here. Okay, either in meter cube or millimeter cube you can keep. If possible, you can write this. 1 liter is equal to 1000 meter cube. That's why. So 1 liter and this 1 by 1000 meter cube is equal to liter. So 1000 liters is equal to 1000 liters is equal to 1 meter cube, and 1 liter is equal to 1 by 1000 meter cube. So 1 liter I have converted into 1 by 1000 meter cube. So 1000 liters is equal to 1 meter cube. 1000 liter is equal to 1 meter cube. That's why this is the conversion. If they are asking us to give the change in the volume in liters, particularly if they mention liters, then only you think about this. Otherwise, change in volume in millimeter cube or meter cube, that is enough. Okay. So in this way, from the basic conditions for stresses, strains and volumetric strains, we have completed a problem involving all the concepts up to the volumetric strain. And then we came into the next concept, which is joint efficiency, right? So in case of the joint efficiency, what we have observed? So in case of joint efficiency, we have said there is a connectivity between circumferentials and longitudinal members. As it is not a single sheet or single member like the structure, I should have to observe the connectivity. As the cylinder original member is strong, but if the joint is not strong to keep the container as it is, what will happen? The bursting may happen. That's why we have got into the concept of joint efficiency. And in case of longitudinal side, longitudinal joint efficiency, when you indicate it with eta L, circumferential joint efficiency it will come with eta C. Okay. If these two terms they are using, now when the stress generated in the circumferential joint, okay, the stress generated in the circumferential joint is equal to, original formula will be as it is, P D by 2T into, only thing added is, when C is here, L will be added, efficiency of the longitudinal joint. Circumferential stress generated, how much is the circumferential stress generated? Based on the joint efficiency in the longitudinal direction. Because we said the circumferential stress is acting tangential to the circumference, and there the connectivity is like this. In the longitudinal direction, one bolt will be added to the upper hemisphere and the lower hemisphere, right? So these spheres will be connected, and those joints efficiency is, longitudinal joints efficiency is involved. Okay, PD by 2T eta L. And in case of longitudinal stress, the original formula is as it is, PD by 4T, but in the denominator eta C will come. What is happening? As the longitudinal stress is appearing like this, and the cylindrical circles like this. This is a circle, and above this one circle is being attached, and the connectivity is in the circumferential direction. Along the circumference, the bolts or the rivets will be fitted along the circumference. That's why the joint efficiency of the circumference came into the picture. Okay, so PD by 40 eta C, and which is equal to sigma L. Okay, using these formulas, using the concept of joint efficiency, we will solve the next problem. Okay, now I am going into the next problem. See here, a cylindrical tank of 750 internal diameter. So the internal diameter they have given is 750 millimeters only. Okay, and its thickness of the member is 12 mm. So 12 mm thick sheet is used to prepare that particular cylinder, and also it is having a length of 1.5 meters. Okay, so this is the way 1.5 meter length is designed, and it is completely filled with oil which is having a specific weight of 7.85 kilonewton per meter cube, and at the atmosphere pressure. If the efficiency of the longitudinal joint is 75%, so eta L longitudinal joint is 75% means 0.75. When you are substituting into the numericals, you should have to convert it into decimals, then only you should have to substitute, not with the percentage. Wherever, simply like our degrees. Okay, so 30 degrees, sin 30 degrees we will indicate, and when I am indicating the 30 degrees into any multiplication directly, like some r into theta, there we will use the theta as radians. So when the direct multiplication is happening, we should have to come here also the same thing. When I am applying for the direct multiplication, I should have to apply the corresponding decimal without giving the percentage indication. And also they have given circumferential joint is 45%. So eta C is 0.45. And find the pressure head of the oil tanker. So what is the pressure head in the oil tank? That we should have to calculate. And also calculate the change in volume, taking the permissible tensile stress in the tank plate is 120 megapascals. So the corresponding permissible stress, the tensile stress which the material of the tank can handle, the stress which the material of the tank can handle is 120 megapascals, which is 120 into 10 power of 6 pascal. So after removing, I can write 120 Newton per mm square. Okay, now the capital E, Young's modulus is 200 gigapascals and mu point is same like the previous data, but here they have given giving some condition which is for joint efficiency also, and they are saying some different things, but they are not even direct. So firstly, everyone will say like this is the pressure offered by the fluid and what is the stress generated in the material. Okay, now I am saying this is the permissible limit of the stress that the material of the steel can handle, and how much is the pressure, how much is the pressure it is handling, what is the fluid's pressure. So from the permissible limit of the stress in the material, or generally from the fluid pressure, what is the stress generated in the metal. Okay, this is the fluid pressure. What is the stress generated in the metal, that is sigma C and sigma L. Those will calculate using PD 2T, PD 4T. Okay, but here what is the thing they are giving? They are giving this stress only my metal can handle. This stress in tensile nature our metal can handle. Now what is the corresponding pressure I am observing by the fluid? Okay, so up to which pressure I can give to the fluid. Now let P be the maximum permissible pressure in the tank. So I am assuming P is the maximum permissible pressure in the tank. Firstly, then we can directly say, what we can say, the longitudinal stress and circumferential stress were limited to, okay, longitudinal stress or circumferential stress were limited to have up to, longitudinal stress is having a limit up to sigma L, sigma C. Its limit is 120 Newton per mm square. Yes, because the maximum permissible tensile stress limit of the material. Now, the corresponding maximum pressure I can give to the tank. So, taking 1 times sigma L, 1 times sigma C is equal to 120. Okay. Firstly, taking sigma L, the longitudinal stress in the metal, if it is equated to 120 megapascals. Okay. So, this is 120 Newton per mm square is equal to PD by 40 into eta C. Because they have mentioned the problem eta C we should have to use. Yes. So, that is PD by 40 into eta C. 120 is equal to P. Just now I am thinking that is the pressure offered by the fluid. The maximum pressure that offered by the fluid. Okay. P into D diameter 750 divided by 4 into T of 12 and eta C the circumferential joints efficiency is 0.45. So substituting all the things, I have got the pressure that may appear in the fluid as 3.456 megapascals. As it is, the output I got is 3.456 Newton per mm square only the answer. Only for final output I am replacing Newton per mm square as megapascal. Pascal is Newton per meter square. Megapascal is Newton per mm square. Because of the conversion it is reducing. Okay. The next thing is making the maximum limit of the stress which is equated to circumferential stress in the member. Okay. That sigma C is equal to PD by 2T into eta L. So sigma C, which is 120, and P is the unknown, which is the maximum permissible stress limit in the metal sheet, and D, internal diameter of 750, and 2 into T. T is 12, and the eta L I have got as 0.75. See here the longitudinal efficiency of the joint. Okay, so P, from this I have got the P as 2.88 megapascals. Okay, see here I can give up to 3.456 for handling in the longitudinal direction. But if I choose this P as here, and the sigma C or the corresponding stress will be raised. Then the stress is equal to the longitudinal stress. When the stress is equal to the circumferential stress, I have got two pressures of the fluid. In those two pressures of the fluids, I should have to choose what is the least pressure. That only I can give to the fluid. Okay. So in these two, the least value of the pressure is the 2.88 Newton per mm square. Up to this pressure only I can give to the fluid. Up to this pressure only I can give the pressure to the fluid. So this is pressure we can give to fluid. So this is the highest pressure head. Why this is the highest? If I cross this pressure, maybe a 3 MPa I have offered. What happens if 3 is there? The corresponding stress generated in the metal will be increased. See here, as P is increasing, this will be increasing. But I am having the limit of 120. Here, when I go up to 3, no problem. Even more up, no problem. So I can give below 2.88 so that every stress will be satisfied, because this is having enough limit. So in the longitudinal direction stress is less, but in the circumferential direction the stress is more, and that I should have to control by reducing the pressure of the fluid. Okay, so I should have to consider least of those two values as the maximum permissible limit of the pressure I can apply. Okay, so in this way I am calculating these conditions, and if possible you can go with the volumetric strain of the member, same like the previous one. So here we have got P answer. What we have finalized? 2.88. Okay. So P is equal to 2.88 Newton per mm square. And internal diameter we have got 750 mm. And thickness they have given us 12 mm. And from this P, D and T, you can calculate sigma C and sigma L. PD by 2T eta L. PD by 4T eta L. Okay, so in this way you can evaluate these two answers. Once you calculated these two answers, you can go into eta C. Once you calculated these two answers, no need to remember efficiency. Once this is over only. So from these two answers, you can calculate the corresponding strains in the longitudinal and circumferential strain. Yes, those longitudinal strain and circumferential strain I can evaluate using those two answers. Can we calculate the volumetric strain? Yes, that also we can calculate, and into volume of the fluid will give the corresponding change in volume. Okay, so the only thing is which is the pressure I can give to the fluid. This calculation is very, very important. Once how much is the pressure I can give to the fluid I know. After that I can calculate the corresponding stress generated, strains generated, corresponding volumetric change. Okay, so this is the way we are solving for the numericals on a thin cylindrical shell, including efficiency of the joint, and also we have given another problem which is involving all the basic concepts like stress strain and volumetric strain. Okay, now I am going into the next topic of our chapter, which is thick cylinders. Okay, so the next concept is thick cylinders. So already we have mentioned this classification. The thickness of the cylinder is large compared to that of the cylinder, which is, in case of the thick cylinders, the metal thickness T is more than that of D by 20, where the D is internal diameter of the cylinder. Yes, if the thickness of the cylinder is more than D by 20, the internal diameter divided by 20, that quantity I have got something, but the thickness is more than the quantity of this ratio, then that thickness is more, the corresponding cylinder I will name, or we can name it as thick cylinder. Okay, now the magnitude of the radial pressure, as we have left this radial pressure in our thin cylinders, but here this radial pressure is considerable. Okay, so there we have observed only circumferential stress and longitudinal stress, but here radial pressure is also considerable. Okay, the magnitude of the radial pressure is large and hence it cannot be neglected. Okay, the circumferential stress is also not uniform across the cylindrical wall. As I have said in the previously, we have taken the example and mentioned the circumferential stress is longitudinal direction as the fluid is offering upward. Okay, the fluid pressure is offering in the upward direction, the circumferential stress is acting in the tangential direction. Okay, in the resisting nature. Okay, as the fluid is trying to burst, and in the resisting nature the circumferential stress is generated. And here the magnitude of the radial stress is large and it is considering, and also the circumferential stress is also not uniform across the cylindrical wall. Okay, so on this cylindrical wall, at every point the circumferential stress is different. It is varying based on the different conditions offered onto the tanker. Okay, so the radial stress is compressive in nature. Yes, this we have already observed. Why it is compressive in nature? Because even though it is trying to expand the body in this way, but this compression is offering and it is causing the metal to reduce. The thickness is getting reduced because of the expansion. Only the diameter is increased because of the circumferential stresses, and due to the radial pressures, even though that is causing like this, but the metal thickness or the corresponding thicknesses may reduce, or the dimensions will be reduced. That's why the radial pressure is compressive in nature. And the next thing, the circumferential and longitudinal stress are always tensile in nature. Yes, this circumferential stress is causing increase in the diameter, and the longitudinal stress is causing increase in the length of the body. Okay, so these are tensile in nature. The next thing is radial stress and the circumferential stresses are computed by using Lami's equation. So for the thin cylinders, there is no special particular equation or the special particular theory, but for the thick cylinders, we are having Lami's theorem or Lami's equation. This is very important for the thick cylinders. Okay, they will directly derive the Lami's equation or Lami's theory for the radial stress or the radial pressure and the circumferential stress. Okay, so for calculating this radial stress and the circumferential stress, we are using some conditions which are generated by Lami's. Okay, the first thing, whenever we go into any theory, we should have to observe what are the assumptions that particular scientist has taken before entering into the concept. Okay, those assumptions I am dealing here. So the first thing is, plane sections of the cylinder normal to its axis remain plane even after under pressure. Same like the bending action. What is happening? Before that, the beam was like this. Okay, so initially the beam is like this, and whenever you observe any cross section, it may appear plane. Okay, like a vertical sheets placed one over another. Okay, like your notebook. So one paper was placed like this. So every cross section is plane in nature. Now after bending, it will take the shape like this. But even that also, when you observe that particular section, it may bend, but the plane is still plane in nature only. Here also the same thing. Initially, the cylinder's section, every section along the thickness, okay, plane sections of the cylinder normal to the axis remains plane and normal even after the pressure. Okay, so when you observe the cylindrical container and when you see any planes which are normal to the axis, when this is the axis of the cylinder, see here, when you write anything, the longitudinal direction is the axis of the cylinder. Okay, now perpendicular to the axis of the cylinder, so many planes were there. Okay, so even after bulging, after the radial pressure application, those planes are still plane and they are still being normal to the axis of the particular cylindrical container. The next thing is the longitudinal stress, which is sigma L. The longitudinal stress is sigma L and the longitudinal strain epsilon L. Okay, remain constant throughout the thickness of the wall. So what are the things they are asking us to change? They are saying radial stress and circumferential stress will change, but not the longitudinal stress and longitudinal strain. So this one more assumption you should have to remember. Longitudinal stress and longitudinal strain are not at all changing at any point throughout the thickness of the wall. So along the thickness of the wall, the longitudinal stress and longitudinal strain are not changing. Initially they mentioned about the sections. So the different sections initially normal to the axis of the cylinder are remain perpendicular and normal to the axis even after the pressure application. The next point is, as I am having three different types of stresses, firstly circumferential stress, next one is longitudinal stress, and then the radial pressure. So in this, circumferential stress will change from point to point along the thickness. Radial pressure is also having the same nature as we have started in the previously, because outside will have zero pressure when it is kept in the atmosphere, inside will have the fluid pressure. So from point to point, the pressure at different points along the thickness is changing. But the longitudinal pressure, what is the longitudinal stress? It is there. That particular longitudinal stress is getting constant or being constant over the thickness, okay, thickness of the wall. So the longitudinal stress sigma L, the corresponding output only this sigma E, right? So sorry, epsilon L. So this epsilon L is also remaining constant throughout the thickness of the wall. And the next point, since the longitudinal stress sigma L and the longitudinal strain are being constant, it follows that the difference in the magnitude of the hoop stress and the radial stress at any point on the cylindrical wall is constant. So how it is happening? As we have said, in the previous condition I have observed only two stresses are applying on a body. Now three mutually perpendicular stresses or three different stresses are acting on a particular body. As I am applying or observing along the one direction, longitudinal strain direction, and sigma L is constant. And what is the next output? The difference between hoop sigma C and PR. So the difference between PR and sigma C is always constant. Okay, in this way the next output can be the next assumption can be made. So the first assumption is regarding the sections, they are always normal to the axis of the cylinder. The next is the longitudinal stress and longitudinal strain are remaining constant even though the circumferential stress is changing from point to point. Radial pressure will also change from point to point. Internally, it will have the internal pressure of the fluid. Now, the next or the third assumption is, as the fluid or the as the longitudinal stress sigma L and the longitudinal strain epsilon L are being constant, and it can be said or we can say that the difference between this PR and sigma C, okay, the difference between the hoop stress and the radial pressure are also being constant. Okay, the difference between radial pressure and the circumferential stress, this hoop stress or the circumferential stress is always constant. That's why the difference constant is still maintained so that the strain is not changing. Okay, and then the material is homogeneous, isotropic, and it is obeying the Hooke's law. So firstly, homogeneous, from point to point, wherever you go, along the length, along the depth, the same natures will be observed. Okay, so along that from point to point. So when you observe Young's modulus, Poisson's ratio, like that. So it will have along the length, along the depth, nothing but along the thickness. So it will have the same property. And isotropic means at a particular point in all the directions, even if it is x, y, z. So Ex, Ey, Ez, mu x, mu y, mu z. So Young's modulus in the x direction, y direction and z direction, Poisson's ratio in x, y and z direction, or any other material constant in all the directions at a particular point is the same. So if you want to stretch in this way, it will respond like the same. If you want to stretch it in this way, it will respond like the same, because it is having the same Young's modulus, and also it is obeying Hooke's law. So what is the Hooke's law? When I am filling the fluid pressure is the fluid inside, and once I take out that, it should have to get the original shape and condition, giving the stress generated is directly proportional to strain. Okay, so the stresses are within the proportionality limit. Okay, as I am applying the corresponding stresses within the proportionality limit, and the corresponding strain generated will be automatically in the straight line, sorry, directly proportional relation. So the stress and strain are in directly proportional relation within. I am applying the stress within the proportional limit. So if I am exceeding the stress, it may not give the proper equation, because in our stress strain curve also we have observed up to certain portion it will give the curve shape. Why it is giving? Because I am crossing the stress limit. Once I cross the proportionality limit, it will not give direct relation. Sigma is direct proportional to epsilon. Such type of conditions will not be there. Only the things which were there were. So these 2 points are helping us, and it is giving the shape of. And the last assumption is like this: homogeneous, isotropic, and the material of this particular cylinder is obeying the Hooke's law. Okay. The next thing, so as we have covered our assumptions, the first is regarding the cross sections or the normal sections in the cylinder, and the next thing I have observed the longitudinal stress, and the longitudinal strain is always being constant along the thickness of the cylinder. And nextly we came into the next thing, which is so the longitudinal stress and longitudinal strain are being constant, means the difference between the circumferential stress and the radial pressure are always constant. And finally, the material is homogeneous, isotropic, and it is obeying Hooke's law when I am applying the pressure within the proportionality limit. Okay. So in this way, the Lami's theorem assumptions were cleared. Okay. Now I am going into the equation or the derivation for the Lami's equation. Okay. So Lami's equation for the radial pressure and circumferential stress only. Okay. This is not for the radial, because radial is a constant. We will get in the last. Okay, this is radial pressure and the circumferential stress only I am giving. Further, I am taking a thick cylinder. Okay, so see here, this is very thick in the cylinder, and inside radius is R1 and outside inside internal radius is R2, and the external radius of the particular cylinder is R1. When you see the hemispherical shape, you can observe like this. It is having a hemispherical head like this, and it is appearing like this. So the pressure is offered onto the walls, and the fluid is causing some pressure onto the walls. Okay. So what is the main condition for the thick cylinders? The main condition for the thick cylinder is its thickness. The thickness of the cylinder is more than d by 20, or you can write 2r2 divided by 20, because I have considered this. Now consider a thick cylinder of external radius R1 and internal radius R2 and containing a fluid under a pressure P as shown in the figure. Yes, we have observed the picture as it is. So I am considering a this is having a fluid which is causing a pressure of P, and let capital L is the length of the cylinder. Okay, it is having some length, it is having some fluid, and it is having internal radius and external radius. In that, I am considering a small element. For this we will explain later in the next step. Okay, consider an elemental ring of radius small r, and it is having the thickness as delta r as shown in the above figure. Let P and P plus delta PR be the intensities of the radial pressures at the outer surface and inner surface and outer surface of the rings. Okay, so see here, see the first picture only. Okay, so this is the original structure, and this purple is indicating the main lines. Okay, these purple lines are indicating the main cylinder. In that cylinder, at a radius r from the center, I am considering an elemental ring. Okay, so from the center at the radius r, we are considering one cylinder. See here, from this point to this, I am having a radius of r, and At this radius r, I am observing a pressure as the internal pressure as PR. Okay, at this radius r, at this level, the internal pressure offered by this is PR, and the thickness of this is delta r. So this is the cylinder. Right. So from the center up to this one is R2, right? Okay. And from the center up to this radius is R1. Now from the center at a radius of R, we have chosen an elemental ring and it is having a particular thickness as delta R. Okay, so at this level we are considering. At this level, when you see this, at this interior level, what is the pressure offered? That I am indicating as PR. Pressure at R radius. Okay. So, radial pressure at R radius. And when you observe at this level, when you see the pressure, I have indicated as PR plus delta PR. Okay. So, these are the pressures we have indicated. Okay. Consider an elemental ring of R radius and delta R is the thickness as shown in the picture, and PR be the PR and PR plus delta PR. PR on this internal side of that particular elemental ring, and delta PR be the intensities of the radial pressures at inner and outer faces of the ring. Only on that particular small elemental ring is there, right? So on the in face of the ring and outer face of the ring, I am observing these pressures. So inner face I have observed PR and outer surface we have observed delta PR, P plus delta PR. Now considering the longitudinal section XX. Okay, so this is the whole surface area. I am considering the longitudinal section XX of the particular ring only. See here, when you see the cross section, this is the whole body appearing. Now I am taking this normal, this ring only, and cutting in this diagram. Okay, so this cylindrical ring I am cutting, and when you observe the bottom hemisphere, it may appear like a circle with R radius and external radius as in R plus delta R, because that is the thickness, right? So this is R and this is R plus delta R, and internal fluid pressure is PR and external fluid pressure is PR plus delta PR, and the particular length of the particular segment or the pipe is L length. Okay, now consider the longitudinal section XX. So see the circle is like this, and along the XX section when we cut, and observing only that ring only, not the whole cylinder, only that particular elemental ring at R radius only I am observing, and the bursting force is evaluated by considering the projected area. What is the bursting force applied? Which is equal to 2 into R into L. See here, this way we have already generated what the fluid is offering with a dimension as a rectangle like this. On this surface, this is P 2R into L. So the bursting force is evaluated by considering the projected area. What is the projected area here? This is the projected area here. Okay, this is my projected area. Onto the projected area, and for the inner face 2 into, and this is the projected area for the inner face, and for the outer face up to this I should have to consider, right? So this is the area that is involving when it is coming for the projected area. Now that area is 2 into R plus delta R into L for the outer surface. Okay, so in surface it is and for the outer we are having one more rectangle, but it is r plus delta r plus delta 2 times r plus delta r into length, 2 times r plus delta r into length. This is the projected area of the particular rectangle for calculating the bursting force. Now the net bursting force is equal to PR, inside pressure of the fluid, as the inside pressure is causing like this, and from the outside there is a reverse pressure is offering, right? So this from this in this direction, PR into the corresponding projected area. This is PR because PR is acting like this. So PR is acting on that internal area, and PR plus delta PR is acting in the outside. That's why the net bursting force is equal to PR into 2 times R plus L minus PR plus delta PR into as this area. Now with the rearrangement, we have got this term as PR 2 times RL. Simply multiplication and cancelling whatever the terms they are common in both the terms. Okay, so finally I have got minus PR and delta R and minus R delta PR minus delta PR into delta R and 2L. Okay, now the bursting force is resisted by the hoop tensile force developing at the level of the strip. So what we have said, this is the net bursting force. So some fluid is offering from inside, some fluid is offering from inside, and some fluid is offering from the outside, nothing but the from outer wall. Okay, how much force it is coming? That is PR into 2R into L. What is the force acting from the outside? That is PR plus delta PR into 2 times R plus delta R into L. Okay, so this is the multiplication of these two terms, and net value we have got, and bursting force is still resisted. This bursting force, how much is the bursting force offered by the fluid, is being resisted by the corresponding hoop tensile force. Okay, that corresponding hoop tensile force. What is the hoop tensile force? Again, you can observe this same picture. What is the connectivity still there? Only this portion was connected. Okay, the metal which is connected is this portion. So what is the area of the metal that is connected? The radius, delta R thickness into L length. Such type of rectangles 2 were there, and this area is being resisted by corresponding circumferential stress. So sigma C into 2 into delta R into L. This is the area which the metal connected. 2 ways were there, so 2 times delta R into L, and the corresponding sigma C was there. Okay, now the bursting force is being resisted by the hoop tensile force, that Fr is equal to sigma C into 2 times delta R into L. Okay, as this net stopping force or the resisting force is equal to net bursting force onto the body. Now equating those two terms for the equilibrium, bursting force P is equal to resisting force offered by the hoop stress, and equating those two terms, and finally neglecting, as we have already said, when you multiply decimal type values, maybe some decimal values, when you multiply, it will give the output even more smaller. So as I am considering this delta PR, delta R, all these things are very very small. When the multiplication or higher power will cause even more lesser quantities, that's why I am negating those smaller quantities. After removing those smaller quantities which are having double power, and finally we have got delta PR into delta R, and sigma C is equal to minus PR, and as it is the remaining term R into delta PR, simply rearranging and neglecting the terms which are in very large quantity, and the longitudinal strain is always constant, and sigma C term will be evaluated like this. So the longitudinal strain and circumferential strain, these calculations will go in the next class. So with this we have completed the equation for the hoop stress or the circumferential stress. Thank you.